AP. Then some points. We get the action that is 1 by tau by x. Yes. Plus. Then that's how I'm going to give it to the DC motor. For simplicity, we put this as only A. Okay, the DC motor constant. The signal is the output coming from the controller like of T. So this is our C of T. And UAT, negative feedback. So what's the purpose input command given? Input command given 500 input command is to raise the speed from 0 RPM to 500. Okay, so for the evaluation, we have observed error signal. So we focused on the signal C of T, twin current signal. Okay, now for the response of the DC motor, we have evaluated C of T as 500 RPM into 1 minus 0.5 times e to the power of minus t by 2 times tau y into u of correct. That's our C of T. And then we have reduced error signal E of T, that is error signal E of T, that is 250 RPM into 1 e power minus t by 2 tau I into u of T. Right? Two important signals with respect to the PA controller. So the intention of using the integral control action only to bring down what the steady state error to 0. Okay, to improve the steady state performance, to improve the steady state response, all by bringing down the ESS to 0. Okay, that is what it was exactly doing in this loop, the PA controller loop. The closed loop control system to control the speed of the DC motor. The input command is 500, exactly the output response is equal to the 500, so error will naturally go to 0. Okay, now the important focus now is what is the signal coming from the integral control action. What is that? M I of T. Let us find out M I of T now. Okay, we know the signal E of T, so what do we find? What is exactly coming from this integrator, so that we can find out the integral contribution. How the integrator adjusts its output. How the integrator adjusts its output till the error signal becomes 0 in this loop. Okay, right? So it's to understand the integral control action. Let us evaluate Mi of T. What is Mi of T fundamentally? Mi of T is fundamentally Mi of T is equal to A1 into A into AP. That is the signal. Okay, so the signal is after passing these three elements. What is the signal? K1 A AP into E of T. Okay, that is the signal as well. Okay, there is the input signal to the integrator. Therefore, Mi of T will be K1 A AP. Then integral of your error signal. Okay, otherwise integral of this error signal 1 by tau y integral of K1 A AP into E of T. Integration with respect to integration for the period 0 to okay, evaluate now. And for me to Kp equal to 1. We know Kp is taken as 1. We know K1 equal to 1 by 1000 whole square RPM. If A is equal to 10. Error is also available. So first get the signal K1 A Kp into E of T first. Okay, multiply this along the error signal. Okay, putting it K1 is 1 by 1000 If P is 1 into the error signal, that is 250 RPM into e power minus t by 2 tau. It's valid for t greater than or equal to 0. Yes. The signal becomes the signal K1 AP into E. Now P becomes RPM will get cancelled, right? 250 divided by 1000 is 0.25 into 10 will be 1.5 watts. What is the unit? RPM will get cancelled. What only unit remains? Volt. So the result 2.5 volts into e power minus c by 2 tau y into u of t or valid for t greater or equal to 0. That is this. So then we have to integrate this signal with respect to time over the period 0 to t. Then substitute. Okay. Substituting the signal curve given here, that is 2.5 volt into e power minus d by 2 tau I into this to the integration. That's what MI of can do this in S domain also, but since error is available in time domain, I am performing time domain integration. Otherwise, what's the other route? Other route is derivative MI of yes. Derivative MI of yes. Now, applying partial fraction expansion and then get into time domain by applying Laplace transform inverse. That is also the route to get into MI of t or to find MI of. Okay, that's one more route. Instead of taking this route, since error is available, we take the time domain integration so that you can understand how the integrator integrates direct signal in continuous time domain and increases its output till error becomes 0. Okay, right. Let's integrate it now. Find out this process. So 2.5 is common, therefore MI of t will be 2.5 volts divided by tau y. The remaining is integral of e power minus t by 2 tau y over the period 0 to t integration with respect to time. You know the integration, so the result is 2.5 volt by tau y, and then what's integration? E power minus t by 2 tau y divided by minus 1 by 2 tau y, the lower limit 0, upper limit t. Okay? What's the result there? It is volts, right? It's 2.5 volts divided by tau y. Applying the limits. Okay? So, one thing will get cancelled for that. This tau y here, tau y will get cancelled, 2 will come to the numerator. So, instead of this, what we can say, it is 5 volt, but minus sign is there. Okay? Upper limit will be with the minus sign, lower limit will be with the minus of. Minus will become plus. So, what is the lower limit? 0. E power 0 is 1. Lower limit will produce positive number, upper limit will produce negative. Therefore, the net result will be 1 minus e power minus t by 2 tau. 1 minus e power minus t by 2 tau y. It's valid for t greater than or equal to 0. That is a contribution coming from the integral control. Therefore, the final signal mi of t, the signal coming from integral control action reduces to 5 volt into 1 minus e power minus t by tau y into e of important signal. The main signal of our interest to understand how a T control action works. Okay? So the actual signal to the integrator is in volts, correct? From the signal 2.5 volt in e power minus t by 2 tau y. That is what integrated by this integrator or integrator and producing this omega. Okay? So this is error in RPM, but actually the integrator gets error in voltage and integrating the voltage error signal and producing output and voltage signal. Okay? Plot all the three signals now. We have to plot where C of t, mi of t along with then we come at r of t. Okay? Take the command going from 0 RPM to 500 RPM. your R of 2. Then immediately get the error signal. What is your error signal? Otherwise, immediately get your C of t. How C of t responds for this? C of t is jumping from what? 0 to 250 rpm. Okay? Because to this point, no contribution from integral control action. So 0 to, since it is almost like a zero order system, that's why jumping from 0 to 250 and then exponentially raising to what? 500 rpm. Up to some time it reaches 500 rpm. Okay? And during this period, what is the error signal? Error signal. Error begins with 250 rpm. Begins with 250 rpm and then the C of t increases further. Error increases to 0. By the time C of t reaches 500 rpm, error goes to what? 0 rpm. Finally, error reaches 0 rpm. This is in fact your ESS. This is in fact CSS. Okay? Steady state output response and steady state error response. And then the signal contribution from the MI of t. MI of t doesn't contribute anything initially. MI of t doesn't contribute anything initially. Why? Time t equal to 0. Equal minus 0, yes. 1. 1 minus 1, 0. It begins with 0 and goes to 5 volts. Okay? It begins with 0 volts. That's your MI of t. Begins with 0 and then exponentially raising it to what? 5. By the time the error reaches 0, by the time your C of t reaches 500 rpm, at the same time, MI of t reaches what? What time it reaches? Steady state t equal to 10 times tau I, where you get e power minus 1. Okay, so all are having the same time events. What is that? 10 times tau I. 10 times tau I. C reaches steady state, error reaches steady state, even MI reaches steady state. What is that? 5 volt consumer MI under steady state condition. Consumer controller contribution at steady state. Integral controller contribution at steady state. Yes. Here are the blues. C of t. Start with the error signal. E of t. Where this one is and I of the how this loop works. Zero order. No integral action. What is the dynamics? Nothing coming from the integral action. What is the dynamics? What was not having any dynamics? So the entire book is having only zero order dynamics. That's why a zero order system can instantly follow your command, but CY are equal to half. That's why it's not going to 500, it is jumping to 250. That explanation will be given in the last class. Correct? Why CR is jumping from 0 to 250? Because of zero order dynamics. Because the effect of integrator, see the effect of integrator at time t equal to 0, nothing. Nothing coming from the integrator. That means the remaining system is only what? Zero order. That's why. Okay? That's why it's jumping from 0 to 250, and then later on exponentially raising from 250 to 500. Okay, right? So when the input command is 500, we know one integrator available in the system can make the output response exactly equal to 500 RPM. So error can move to 0 since we have an integrator in the loop. So the output response will be 500 RPM at steady state. Yes, this is also going to be what? 500 RPM. Therefore, steady state error actually goes to 0 RPM. Therefore, the signal is 0 volt. The signal is also 0. The signal also 0. No contribution, but the motor is running at what? 5 RPM possible. Only when the input signal is 5 volt. That's why the integrator acts exactly 5 volt at steady state. Okay? Because the integrator somehow understands what is the input command? Always sensing. Always sensing error signal. As the error signal keep on decreasing, only because of integral control action. As the integral control action keep on increasing its output, giving extra input signal to the DC motor that decreases your error till error becomes 0. Till error becomes 0, the integrator keep on adjusting its output. The moment the integrator output becomes 5, error goes to 0. The moment error goes to 0, the integrator stops. It's changing its output. Then the moment error becomes 0, it stops at what? 5. It understands. That's how it understands. The loop means exactly 5 volt because the input command is only 500 RPM. Motor means only 5 volt running speed and surrender mode at 500 RPM. So it stops at 5. Suppose if it is 400 RPM, it will stop at 4. If it is 600 RPM, you will understand intelligently this is going to stop at what? 6 volt. That's how the integrator adjusts its output till its input signal becomes 0. Integrator is not worrying about this error signal. Integrator worries about only its input. So when this input signal becomes 0, the error signal becomes 0, then naturally the integrator input also becomes what? 0. Then the output starts at this level. Okay? That is equal to 5 volt in this case. Alright? That's how very intelligently the integrator works. Okay? And always brings down the steady state error to 0. Okay, that's the rule given to integral control action. Purpose of integral control action? Improve the steady state performance always by targeting what? Steady state deviation. That's a conclusion. A very good example to understand the role given to integral action. Okay? Is it? So we plot two more signals. Okay? And so far I have given the significance of tau I, but I didn't play the any value of tau I. Let us play some values of tau I will see. Now we are going to play with only two signals. One is the error signal and the one is for the given error signal, what is given? Mi of t. We focus on only these two. Okay? Error response and correspondingly the integral control action response. Okay? This is your error plot. And this is the output coming from integral control action. Okay? Listen to this. I'm going to plot only two signals. One is Mi of t, integral contribution. Another one is your error signal D of t in RPM, Mi of t in volts. T of t, initially beginning with what? 0 RPM and jumping to what? 2 T of t. Let me take tau y equal to what? For time intervals? For time intervals, 10 times tau y for the time taken, 10 seconds. So within 10 seconds, there it decreases from 250 RPM to 0 RPM for t. Within the same period, m of t increases from 0 volt to 5 volts. So 0 volt, beginning with 0 volt and then going to 5 volts. So the voltage, okay, this unit is in volt, this unit is in RPM, but the time even will be same to that. 10, 6. Okay, understand it. So part when tau equal to 1 second, it's how the error signal makes your integrated output increasing with respect to time. As error decreases, even though error decreases, what's the contribution from integrator? It is keep on increasing its output till error becomes 0. Okay, that's why it is understand. So the integrator available in the loop keep on adjusting its output signal till its input signal, which is a function of error, becomes 0. This happens when tau y equal to 1 second, this happens at 10 times tau y, which is 10 seconds. As per the signals evaluated. Therefore, command remains same, only we are changing tau y. Move signal for different tau y equal to for two different values of tau y, 0 RPM, jumping to 250 and then going to 0. Then for a different value of tau y, again the error will begin with the same 250 RPM and then back to reach quickly the 0. So this is probably the steady state, this is probably the steady state, correct? But anyway, it is equal to 10 times tau y. So this belongs to, for example, tau y equal to 1 second. For example, this one, tau y equal to 1 milliseconds. Okay, so what is this time? Settling time, 10 seconds. And this time, 10 milliseconds. Is it? Okay? So at what time error reaches 0, ultimately what's the most given rate in the control action? Bring the steady state error as quickly as possible to 0. So then decided by tau y, if tau y equal to 1 second, it takes 10 seconds, that's a blue, that's a black tau. Tau y equal to 1 millisecond, that's your blue tau. It settles at what? 10 milliseconds. How quickly the error got down to 0? Decided by integral time cost. That's a conclusion. Okay? Conclude how quickly the error got down to 0.